introduction. I've shared my screen. Do you see my slides now?
Yeah, we can see your slides. Thank you.
Thank you for the introduction. I'm Daisuke Hotta from Japan Meteorological Agency, and today I'd like to present one idea to combine machine learning technique with data assimilation, with particular attention to non-Gaussianity issue and data redundancy issue of image data. The goal of this study is to assimilate two-dimensional images like satellite image and radar images. There are many difficulties in assimilating these image data, but three particularly challenging issues that I think are most important are non-Gaussianity and dimensional redundancy and interpixel correlations. By dimensional redundancy, what I mean is that images come in structured patterns so that the actual degrees of freedom that they can take is much smaller than the nominal size of the image data. There are existing strategies to cope with these difficulties. Gaussian Anamorphosis, or GA, can mitigate non-Gaussianity issue, and thinning or linear dimension reduction like EOF can mitigate dimensional redundancy issue. And it's becoming quite common to directly account for non-diagonal component of the R matrix to account for interpixel correlations. But these strategies have their own limitations. Just to remind you, in case you are not familiar with what Gaussian anamorphosis is, let me briefly explain what Gaussian anamorphosis is. The idea is to transform the model state X or the observable Y so that the prior and likelihood distribution become closer to Gaussian distribution, and then perform Gaussian-based data assimilation in the transformed space, and transform the resultant analysis back into the physical space. Gaussian anamorphosis is shown to be very effective in assimilating non-Gaussian data such as precipitation and soil moisture, but it has a drawback. The drawback of GA is that multivariate transforms that can respect correlation among different components of the data is very difficult to construct. So far, Gaussian anamorphosis has only been used in a univariate way. So the interpixel correlation is almost discarded in the application of GA so far. Okay. So coming back to my motivation, we wish to simultaneously achieve these following. One is variable transform that can bring distributions closer to Gaussianity. We wish to also achieve dimension reduction or data compression. We also wish to achieve removal of error correlation. Achieving these three at the same time might seem very difficult, but a solution has already been proposed in machine learning community. It is called variational autoencoder, or VAE. So what is VAE? So here is a schematic illustration. In VAE, we assume this situation. We assume that high-dimensional complicated data X is generated from low-dimensional uncorrelated Gaussian vector Z. And how X is generated from Z is determined by decoder distribution. And how X mapped to Z is determined by this encoder distribution. So there's no one-to-one correspondence. We assume that they are stochastically determined by conditional distributions, probability of X given Z and probability of Z given X. We assume that we can only observe complicated large data X and latent variable Z are not observable. Now, under such situation, we wish to obtain good approximations to these conditional distributions. Now, by learning many realizations of X with VAE, we can obtain approximate conditional probability distributions denoted P theta and Q phi here. And these are both assumed Gaussian distribution, and their mean and variances are neural networks parameterized by this theta and phi. So as you can see from this schematic figure, the encoder stochastically transforms non-Gaussian complicated data into small Gaussian data. So in this sense, VAE encoder can be interpreted as a multidimensional version of Gaussian anamorphosis, which combines data compression as well. So with these nice properties of VAE, I propose to exploit VAE in assimilating non-Gaussian image data. The idea is just to use VAE in place of regular Gaussian anamorphosis. First, we transform the non-Gaussian data. That can be Y or X or both of them. Transform them by the mean of the VAE encoder distribution, and then perform regular Gaussian-based data assimilation in the transformed space, and finally transform the resultant analysis back to physical space by the mean of the decoder distribution. It's interesting to note that encoder and decoder are subject to transformation errors because they are stochastic, but VAE can quantify such errors as the variance of these approximate conditional distributions. So we can incorporate transformation errors by adding encoder variances to the diagonal component of R or B in the transformed Z space. As we will see later in this talk, this is like an automated quality control in the sense that data that were not seen in the training data are automatically assigned large error variances so that they are ignored in data assimilation. So here's a more specific procedure of the proposed method. For now, just for simplicity, we consider a special case where all state variables are observed. before doing data assimilation, we need to train the VAE. And training VAE requires large data sets. So just like regular Gaussian anamorphosis, I propose to use climatological distribution to train VAE. And then by training VAE, we can obtain the encoder and decoder distribution. And from the assumption that all state variables are observed, we can use the same encoder and decoder for both the state variable and observation. Now, at each assimilation step, what we do is to prepare the z-space observation by applying encoder mean to the observation y, and similarly to the background. And then after doing this transformation, we perform Gaussian-based data simulation to the transformed space, but with the following tweaks. These are deviation from a typical use of Gaussian anamorphosis. So what I propose to do is to add y to z encoder variance to the diagonal of R, and also add x to z encoder variance to the diagonal components, the B matrix. Then after doing assimilation in the Z space, we transform the posterior back into the physical space by using the decoder mean. So now to examine how effective this proposed method is, I've set up an idealized experiment which we try to correct position error by assimilation of image data. Here, in this experiment, we mimic a situation where we try to correct tropical cyclone position error by assimilating all sky infrared image data. This is a problem that is particularly difficult for Gaussian-based conventional methods. So we consider these disks with a nice structure, and whose position, center position, is climatologically Gaussian distributed with a variance of 2 center means at the origin. We assume the background is twice more accurate than the climatology, and we assume that observation is even more accurate by a factor of 2, but with displaced mean position. And here is my problem description. We assume that the true latent variables, in this case the center position, and their distribution, and how these images are generated from the latent variables are all unknown. But we have access to a large climatological data set of the observed images. Under such conditions, the problem is, can we correct the tropical cyclone position without distorting this structure by assimilating these images? You might think this is a trivial task to human eyes, but this is actually a very difficult problem, as I show in the next slide. Okay. So in this problem, the true latent variable is center position, and it's Gaussian distributed. So the optimal solution is to assimilate the center position with the canonical Kalman filter. So given a background like this and observation like this, the ideal analysis looks like this. I will use this solution as the reference solution hereafter to show how difficult this problem is for conventional data assimilation methods. Here I'm showing naive pixel-wise ENKF assimilation of the image data. By this naive assimilation, we get this blurry, distorted disk. And we often, when assimilating image data, we often apply thinning to mitigate interpixel correlation. But as you can see, thinning actually doesn't really help the situation with this distorted image. And for the special case of tropical cyclone assimilation, we can do a technique called DC vital assimilation, in which we estimate center position from the image and assimilate center position. But what we end up is this distorted disk. So all these existing methods fail to preserve this disk, this structure. So this is a very difficult problem for conventional DA methods. Now I'm showing the VAE setup that I tried. I generated 5,000 samples from the climatological distribution and trained VAE on this climatological data. The encoder and decoder configuration that I tried is shown below. For the encoder, the input is a 41 by 41 pixel image that maps to intermediate vector with 500 dimension, mapped by dense layer with value activation function. And we map this intermediate vector to the encoder mean and log variance of the encoder, which has 10 dimensions each, again with dense layer and value activation. And then we draw the latent variable from this encoder distribution. The decoder network is just an image, a mirror image of the encoder network, except that instead of value activation, immediately before the output layer, we put sigmoid activation function. So before doing data assimilation, we need to check if the training was successful. And to see that if the training was good, I'm showing here the reconstruction error for training distribution and a sample from another distribution. By reconstruction, what I mean by reconstruction is the result of encoding and then decoding the data. So given this original data, if we encode and then decode, we get this reconstruction. And as we can see from this figure, so the original and reconstruction data are very close. So this means that the training was very successful for this problem. So now I check whether the non-Gaussianity was mitigated by this encoding. I'm showing here the marginal histograms of each component of the encoded data given with climatological input. You can see that these are not perfectly Gaussian, but considering that the pixel-wise marginal distribution of the original data was either 0 or 1, so that they were just superposition of two delta functions. So considering that these are not perfectly Gaussian, but we believe these are very good enough. now, finally, I'm showing what we get by doing data assimilation with the aid of VAE. So given this background and this observation, with the proposed method, the analysis that we obtain is this one, which perfectly preserves the disk structure. So there's no visible distortion to the disk with a nice structure. So it looks very nice. And if we
Daisuke,
compare,
just your time is nearly up. Maybe you
really
can.
running out.
Yeah, your time is nearly up. Maybe you can wrap up your talk.
Okay, sorry. So if we compare the proposed method with the conventional method, the proposed method is much closer to the ideal reference than the others. And earlier in this talk, I said that VAE allows for built-in QC. So here is how it works. So by adding encoder variance to R, and encoder variance becomes large if the input is outlier. So if we assimilate this outlier observation, what we get as analysis looks like this, which is not very different from background mean, which means that observation was virtually ignored. This is a nice property. So to wrap up, VAE can achieve Gaussian transformation and data compression and correlation removal all at the same time. So, and I obtained promising results for this case where all seed variables are observed. Now, if we move toward more realistic situation, there are many problems that remains, but the most difficult one, I believe, is a highly nonlinear observation operator. I don't say much about why this observation operator becomes nonlinear, but if we consider a situation, more realistic situation, but because we use decoder and encoder that are nonlinear, we end up having nonlinear observation operator. So we need to account for nonlinearity in observation operator. And I believe a promising approach is to combine VAV simulation with iterative ensemble performance smoother, because this method was shown to be very effective in handling nonlinear observation operator. So sorry for running up that time. I'd be happy to take questions, and thank you very much for your attention.
Thank you very much, Daisuke, for this very nice talk. So there's one question from Michael Tsirulnikov. So he's asking, performing linear assimilation in non-linearly transformed variables can introduce biases when transformed back. Have you studied this effect?
For my problem, I don't see any bias. Thank you for your comment.
Okay, and just quickly, another question from Arata Amemiya. Are R and B in Z space diagonal by definition? How do you obtain them?
Yes, they are by definition diagonal. And I used ensemble to construct the diagonal matrix.
Okay.
Okay, thank you.